12.4 talks about applications of second order equations. We're talking about spring mass systems. So suppose L is the stretch of a spring beyond its natural length. Keep in mind, this is the natural length. So if that's the natural length of the actual spring, I attach some mass, and it's going to take the spring and stretch it, this capital L. Now, I could push this up or down. So, if I was to pull this down, so I could pull this down or push it up. Basically, I attach the weight to it and I let it stand still, and I measure that L. So that's the stretch beyond its natural length. I could either pull it down or push it up. From this point, right there, if I was to pull it down or push it up, if I am to push it, actually, let's go this way. I'm sorry. Okay. From this point, we call this x of 0. So, if I push it down, that's positive. If I push it up, that's negative. The motion is described by the following equation that's provided on your test. You don't need to memorize that. You just need to know what is what. This letter right there, that's mass, times the second derivative. This is an object running back and forth. I could derive this, but it takes some time and students are not as interested in it. This B, this book calls it B, most books call it lambda. It's the damping force. And this is the spring constant K. That's from Hooke's law. And f of x is an external force. You need to know if there's an external force added to the system or not. Now, do keep in mind, whenever I get weight, that's mass, and this is the mass that we need, times gravity. And gravity, depending whether the problem is given in meters or centimeters, you use 9.8. And if the problem is given in terms of feet or inches, you use feet. It seems this book specifically uses only feet and inches. They really don't use meters and centimeters, so no big deal. So we stick with that. But in case you come across it in the future, that's what it is. Now there's a special case. If there is no damping, if B equals 0, if this piece is not there, then the motion is called simple harmonic motion, because that's simply a cosine and a sine running back and forth with no damping on them. So let's start with some examples. Example 1, we have a 3-pound weight. The weight is 3 pounds. So the 3 pounds stretches the spring 4 inches. So the actual stretch x is 4 inches. That's what the 4 pounds cost. That's what the 4 pounds, the force of 4 pounds cost that much stretch. We need to convert that to feet. And if you remember, each 1 foot is 12 inches. So that's really 1/3 of a foot. That piece of information we like to keep alone or separate. Now we look at the second part. The weight is pushed 4 inches above. So initially, I'm going to take this weight and push it up 5 inches. And if you recall, coming down is positive, so going up is negative. And again, I need to convert that. So the initial position is negative 5/12 of a foot. And released. If you release it, that means you didn't add anything to the system. You just let it run down due to gravity, nothing more. right? If you gave it an initial push down or up, then you would say that's, whatever, feet per second, minute, whatever problem talks about. And the motion of the weight, find the motion of the weight as a function of time. Assume no damping. No damping means V equals 0. So this is what I know. An equation is provided, and the equation reads mx double prime plus bx prime plus kx equal f of x. In this case, I need to find m. Well, we find m by saying, well, let's see, w equal mg. Well, the weight is 3 pounds. Since we're dealing with feet, the gravity is 32 feet, right? 32 feet per second squared. So m is 3 divided by 32. Plus 0 x prime plus, I need to find k. And I'm going to find k by going in and saying, well, alright, let's see. The weight of 3 pounds, so let me write out the formula. Hooke's law, F equal kx. The weight of 3 pounds stretched the spring 1/3 of a foot, which means k equal 9. And there was no external force. They didn't say anything about that. So my equation is really, if I multiply by 32 over 3, this is the equation. If I multiply by 32 over 3 each of those, that will be x double prime plus, if I take 9 and multiply it by 32 over 3, 3 divides 9 3 times, that is 96. That's pretty much the equation I have to play with. And what is that? That's a second order linear differential equation. So how does this whole game play? I would say, well, let's start with, let y equal e to the d, let x equal e to the t d, finally. And then what do I get? I will get d squared plus 96 x equal to 0. So d would be plus or minus the square root of 96i, or j, this looks like j. X equals 0 is useless. So d would be plus or minus, this is 16 times 6, 4 radical 6j. Now I gotta organize this better, yeah, for next time. I'll do it on the right. Okay, and my solution is that x of t is gonna equal c1 times the cosine of 4 radical 6t plus c sub 2 the sine of 4 radical 6t. That is the general solution. Now what? Oh, I used them already. I should have used a different color. Now what? We know that x of 0 is c sub 1. The cosine of 0 is 1. C sub 2, the sine of 0 is 0. And that is a negative 5 over 12. Which means C1 equal negative 5 over 12. Got it. Replace this by negative 5 over 12. And we know that x prime of 0. So what's x prime? X prime is negative 5 over 12 positive times 4 radical 6, the sine of 4 radical 6t, plus 4 radical 2 c sub 2, the cosine of 4 radical 6t. And x prime of 0 would be, well, that's a 0. That is a 1. That will be 4 radical 2 c sub 2 times 1. And that equals a 0, which indicates that c sub 2 equals 0. So this is 0. So my final solution to this problem, the final answer is that if you look at x of t is negative 5 over 12, the cosine of 4 radical 6 t. That would describe this specific system with all of these conditions. And that's how we do these problems. They're all worked out the same. No difference. Here's another one. So let me organize this a bit better. A 6 pound, the force or the weight now is 6 pounds. Stretches a spring 10 inches. So if it stretches a spring 10 inches, that's really L, right? But in this case, they like X. 10 inches in feet. Again, you could write that every time if you really want. I'm going to start skipping that from the next section, from the next problem. So if you divide by 2, the initial is 5/6 of a foot. That's the actual stretch. That's the first piece of information that I need. The second one, the weight is pulled 6 inches below. X of 0 is positive 6 inches, which is half a foot. And then given an initial downwards velocity is positive, upward velocity is negative, of 2 feet per second. All right. The motion of the weight, find the motion of the weight, is assume there's no damping again. We're assuming v equals 0. And I'll write the equation down. I suggest you write it a few times. Again, I'm providing that in the exam so you get used to it. And the equation is m x double prime plus bx prime plus kx, Hooke's law, equal f of x. In our case, we need to find m first. And we do that by taking the first piece of information given. We know that W equal mg. The weight is 6. Mass is what I'm looking for. Since everything is in inches, we are going to use 32 inches and feet. So m is 6 over 32, which means divided by 2, that is 3 over 16. We know that's 0, so that's gone. And we want F. We know that F equal Kx. The force is the 6 pounds. And it stretched the spring 5 over 6. So K is 36 over 5. Times X. And no external force. I need to clear the fractions. So X double prime plus, if I multiply by 16 over 3 both sides, 3 divides 16 12 times. So I'm going to have 16 times 12. You could use a calculator on that, but let's keep it 16 times 12 divided by 5, x equals 0. All right, there's the equation. Now what? Now we know the drill. We've been doing this for a while. let's take, that's all the information that we need. Let x equal e to the dt. Then we know that d squared plus 16 times 12 over 5 x equals 0. That means d plus 16, d squared plus 16 times 12 over 5 what is 16 times 12? $192, if I'm not mistaken. Or x equals 0, well, that doesn't get us anywhere. That means d equal plus or minus the square root of 192 divided by radical 5, which is j, of course, plus or minus. So that's where the 16 and the 14 become very handy. That's a 4. And this is 4 times 3, so the 4 clears as a 2, right? Or that's 64. 2 times 4, that's 8 radical 3 over radical 5j. So my solution set, we know that is the cosine of 8 radical 3 over radical 5x t, and the sine of 8 radical, if you want to rationalize, it's up to you. If you rationalize, that's 8 radical 15 over 5t. Either or. So the last step is to find the coefficients. We know that x of t is c sub 1, the cosine of 8 radical 15 divided by 5t, plus c sub 2, the sine of 8 radical 15 over 5t. That is my general solution. Now I need to find the specific solution due to those conditions in which x of 0 is 16. Well, look at that. X of 0 is c sub 1. If you put a 0 there, that's 1. If you put a 0 there, that's 0. And that is, we agreed that was 1/2. So we know that c sub 1 is 1/2. Use that. We know if we take a derivative, that is going to be negative 1/2 times 8 radical 15 over 5, the sine of 8 radical 15 over 5t, plus c sub 2 times 8 radical 15 over 5, the cosine of 8 radical 15 over 5t. X prime of 0 would be, the sign will give you a 0, will be c sub 2 times 8 radical 15 over 5, but that's 2. So that means c sub 2 is actually 10 over 8 radical 15, which is divided by 2. That is 5 over 4 radical 15, which is 5 radical 15 over 5, 4 times 15, if you rationalize. And that would be 5 divides 15 3 times, radical 15 over 12. So my solution set, or my equation, becomes 1 over 12, the cosine of 8 radical 15 over 5t, plus c sub 2 radical 15 over 12, the sine of 8 radical 15 over 5t. And that would be my final answer. Remember, this is a general solution, and this is a particular solution. So just let's say the explicit solution. So that is the answer. All right.